Welcome. My name is Ron Papa Schmidt, and I'm the creator of the Net Zero Now YouTube channel. This is going to be video 10B in the science section. We're going to talk about the atmosphere, and then specifically we're going to talk about atmospheric circulation. This is going to be part 2. We did a part 1 a little bit earlier. And we're going to continue the discussion we started in part 1. So the first question we're going to address is, what is the structures of Earth's atmospheric circulation and how does it operate? And then the second thing we're going to address is, how does climate change impact Earth's circulation? So let's begin. In part 1, we talked about the Hadley cells, the Ferrel cells, and the polar cells. If you hadn't seen that presentation already, I would suggest you maybe view part 1 before you look at part 2. In part 2, in this section, we're going to cover the Intertropical Convergence Zone, which you can see on the diagram here is sort of where the equator is, the horse latitude, the polar front and the related jet stream, and then the troposphere and the tropopause. Now, before we get too far into this, I thought I would show you again a map so you can see where these latitudes really are, because if you're like me, it's really hard to say, well, exactly where is the equator, etc. So the equator, or 0 degrees latitude, sort of runs through the upper part of South America. And then the 30 degrees latitude, or the horse latitude, is sort of at the northern part of Florida and the very southern tips of Texas, New Mexico, and Arizona. And then the polar front, or 60 degrees latitude, is sort of northern Canada. And then it's also the very southern tip of Alaska. I just wanted to show you one other slide we showed here frequently, just in case you haven't seen it in some of the other presentations we do. But the diagram on the right, a chart on the right, shows that temperatures have been increasing. And it's interesting, it shows that temperatures over land are increasing faster than they are over the ocean, and the temperatures in the Arctic are increasing the fastest. And that is sort of verified by this heat map you see on the right, and the left rather. And if you look to the very top, you'll see the brown area, that's the Arctic. And the Arctic, what it's telling us is that the Arctic temperatures have gone up 7.2 degrees Fahrenheit in the last 50 years. That's a fairly dramatic increase. And it does have some implications in terms of our weather patterns, etc. on Earth. So let's get into the specifics. So the Intertropical Convergence Zone, or the ITCZ, is located, as you can see on the map, on the equator. The ITC is what it really is. It's a belt of low pressure, and it's got thunderstorms and clouds that encircle the Earth, basically what they call the thermal equator. And this is where the trade winds from the northern and southern hemisphere meet. If you take a look at the chart, you'll see those sort of bluish, greenish line, light greenish lines there that are pointing from east to west, and they sort of meet at the ITCZ. And that creates this area, which is sometimes also called the doldrums, because it's so calm and it has windless related kinds of conditions. So if we go on about the ITCZ, it was created because the equator, or the region of the equator, receives intense year-round heat from the sun, which warms the air. And then also warms the ocean water in that particular area. And this warm, moist air becomes buoyant and rises into the atmosphere with the assistance of these converging winds. Because these converging winds are there, it helps cause the air to rise. And as it rises, it expands and cools, causing water vapor to condense, and that forms clouds, and then the result of that is precipitation. Then if you've listened to the podcast on extreme weather, it also then results in thunderstorms and tornadoes eventually, although not in this particular area, cyclones. The ITC follows the thermal equator. And what that means is that in March it starts moving north in the northern hemisphere, which brings wet seasons to the tropics. And in the northern hemisphere, and then in the southern hemisphere, it brings a dry season at that time. And then the process starts reversing in September. And these seasonal shifts drive the monsoon climates you hear about frequently, where we have these seasons of wet and dry. They're really driven by the shift that occurs with regard to the ITCZ, excuse me. Now, to maybe show this sort of visually here, so what causes a shift is the fact that the Earth is tilted on its axis. And so therefore the different areas of the Earth, northern hemisphere and southern hemisphere, get more or less sun at different times of the year. The other thing you'll notice, if you see down below, you'll see the pink line and the bluish line, which represents the ITCZ in different seasons. The pink line is in July, the blue line is in January, and you will notice that it's fairly wide, right? And the ITC can vary in length, by the way, from 50 miles to several hundred miles. And that varies by location, and it also varies by the time of the year or the season. The other thing you'll notice is that they're not symmetrical, okay? And the reason for that is that we have these different temperatures, differences over land and in the ocean, and that causes these kinds of fluctuations also. So let's get to the next thing. So the converging winds and warm ocean temperatures in the ITCZ create conditions for the development of tropical disturbances such as hurricanes, typhoons, and cyclones. And because as our temperatures are warming, for every 1 degree increase Fahrenheit that we get, it means there's 4% more moisture in the atmosphere. And you can see that from the chart on the right-hand side here on the bottom. You can see how we know from previous graphs, I just showed you that temperatures are increasing. You can see that atmospheric moisture is moving along with that. And that means that we can therefore potentially get more intense hurricanes, typhoons, and cyclones because there's more water moisture within the atmosphere. So let's move on now to the horse latitudes. The horse latitudes are subtropical regions located around 30 to 35 degrees north and south of the equator. And they're also known for their weak winds, calm seas, and in this case, so little rainfall. So because these are high pressure systems that are coming in, what happens is it doesn't get as much rain. So like the doldrums, there's little wind here, but in this case, there's basically very little precipitation. The horse latitudes are a key part of the Hadley cell circulation as it cools and sinks down to Earth, and it creates a very high pressure zone in this area. The other thing is the dry high pressure conditions that are the result of this leads to the formation of most of the world's major deserts. And so if you look at a globe at the 35 degrees latitude, both the north and southern hemisphere, you'll see a lot of desert areas. For the northern hemisphere, you'll see the Sahara deserts in Africa, and then you have the deserts of the southwest United States and Mexico, and you have a comparable thing in the southern hemisphere. Climate change is causing, though, the horse latitude to expand poleward. This shift is moving the associated high dry weather patterns into more temperate regions, increasing the risk and intensity of droughts, wildfires, and desertification. And if you take a look at the southwest United States, you can see that happening, right? I mean, look at the last couple of years, just 2025, how many wildfires we've had within these areas, how much drought there is in these areas. And remember, these areas like the Horse Latitude and the ITCTC are not just straight lines, and they also have a significant amount of width to them too. So one other characteristic is that over the last 40 years, the Horse Latitude has been widening towards the pole at a rate of 1/10 of 1 degrees to 5/10 of 1 degrees latitude per decade. That may not sound by much, but that's a lot of miles. Now, let's take a look here. So if you see you can see the ITCZ here. Just think of think 30 degrees above that, and you can see the same kinds of things happening with the Horse Latitude, okay? And you can get a sense of that maybe as we talk about hurricanes a little bit. If you take a look at the graph in the upper right-hand corner, you'll see the yellow and the blue. Those are the trade winds. The yellow would be in the northern hemisphere. And you can see what happens is that you have the warm winds coming off of Africa. They're blowing towards the United States, and they're in the Horse Latitude. And then as they continue to get closer to Florida, sometimes frequently they run into the Westerlies, and they pull them out keep them in the Atlantic Ocean, and we don't get as much storm damage. But occasionally, the winds aren't as strong, and the Horse Latitude, the trade winds rather, get into the Gulf of Mexico, where they further strengthen, by the way, because of the warmth of the water in the Gulf of Mexico. But then the Westerlies get a hold of them and move them up. But in that case, they're moving up through the continental United States. And we have significantly more damage when that happens. So that's sort of what's causing that. And you remember, we frequently have sort of a hurricane season in the United States. The peak season sort of starts around September, and that's the reason for that is the shift that takes place with regard to the ITCZ and the Horse Latitudes, okay? So I want to give you a quick sense for that. So let's get to the polar front now and the jet stream. So the polar front is the boundary between the Ferrel cells and the polar cells around 60 degrees latitude. And you have a clash of air masses that creates steep temperature and pressure gradients along that front. And that's because if you look at the top of the graph up there, you'll see the polar cell, and that's a very cold area coming down, creating high pressure there, which leads then down to the polar front, where it interacts with the warmer air from the Ferrel cells, and it goes up into the atmosphere, and it creates this low pressure area there. Now, the jet stream roughly follows the polar front. And we've talked about the jet stream in some other presentations, so I'm not going to go into it in great deal here. But it's fueled by powerful temperature and pressure contrast along the polar front. And the high Arctic temperatures are causing it to meander. Remember in the earlier graph when I showed you the heat map where the polar region has increased by 7.2 degrees Fahrenheit in the last 50 years? Well, that has it's really temperature differences that drive a lot of these patterns here. And the temperature differences are decreasing between the pole and the equator. And so for the less intense. And as a result of that, you get a more meandering kind of jet stream, as you can see in the map here, the article in the lower right-hand corner. You can see how the jet stream is meandering. And it's meandering more all the time as temperatures rise. The other thing is the polar front is a major driver of weather and the corresponding jet stream. In the mid-latitude area, it's bringing rapidly changing weather patterns, as you know, if you live in this region like I do. And when the dense warm air rises over the cooler and even denser air. the energy from these colliding warm and cold masses creates mid-latitude cyclones and the development of warm and cold fronts, which and the resulting warm fronts then create sort of large areas of light precipitation, but the faster moving cold air pushes under the warm air, creating cold fronts which are more intense, and they deliver a much more intense rainfall and thunderstorms, but they don't probably last as long. And then the next thing here, the polar shifts positions with the seasons, moving towards the equator in winter and the poles in summer. It sort of follows the ITC. And the seasonal migration means that the mid-latitude area sort of experience more storms and more varied weather in winter. So now let's get on to the tropophase and the tropopause. The troposphere, rather, I should say, is the lowest layer of Earth's atmosphere. The average height is about 7.5 miles from the surface, but if you take a look at the diagram in the upper right-hand corner, you can see that in the Hadley cell area, it can be from 10 to 11 miles there, and at the pole, maybe 4 to 5 miles. And this is a home for all terrestrial life. And nearly all weather phenomena occur within this layer. Now, the tropopause is sort of a transition layer between the troposphere and the stratosphere, where air temperatures stop decreasing with altitude and become stable. And that's sort of what limits the vertical mixing of this warm air as it's going up. So it's a very crucial area. And again, its height and other things varies. So it's higher in the Hadley cell area than it is in the Ferrel cells or the polar cell area. Now, what are some key characteristics of the troposphere? One, temperatures decrease with increasing altitude. It is the densest layer of the atmosphere, and it contains about 75-80% of the atmosphere's total mass. Almost all water vapor is concentrated in the troposphere, which is why this is a layer sort of where weather, clouds, and precipitation occur. The vertical mixing there's a vertical movement here, and it causes significant mixing and turbulence throughout the troposphere. So there's a lot of upward and downward movement, and you see that frequently when airplanes are sort of bouncing up and down in flight. This is where air exists, and air is composed of 78% nitrogen, 21% oxygen, 0.9% argon, and again, just 0.1% in greenhouse gases. And another function, the troposphere sort of provides us from small meteorites and other debris from space. So let's wrap this up. So far we've talked about Earth's circulation system and how it works. And we talked about, in part one, we talked about the various different cells and their wind patterns. And then in this part, we're talking about the Intertropical Convergence Zone, the horse latitudes, the polar fronts and jet streams, and the troposphere and the tropopause. So what do I want you to get out of this? Well, maybe one is an appreciation for how dynamic Earth's atmospheric circulation system is, and how important it is to our living conditions here on Earth. So whether we live in a desert area or in a rainforest or in the mid-latitude areas, our weather and other kinds of things are substantially driven by this atmospheric circulation system. And the system is also very sensitive to temperature changes. And you can see that as the temperatures have been rising much higher in the Arctic than they have been at the tropics. So the temperature differences are going down, and that in turn affects how these things behave. So the jet stream meanders more. That means where we're located, we get more variation in our weather. We get these longer periods of intense rain and periods of drought, etc. And weather patterns stay around longer than they did in the past. The other point I guess I want you to get is because of the mass of these systems, there's very little, I think, that individuals or human beings are going to be able to do to correct some of the problems we have. I mean, I don't think there's a magic bullet here. There's not a new technology that somebody's going to come up with that's going to correct the imbalances that are occurring here. It's just too big. It's too massive. And it's just incredibly difficult to model these things. And so we really still don't fully understand all the implications of rising temperatures and other kinds of things. And that's very understandable given the size and complexity of this. So the message is we really need to pay attention to our increasing temperatures, and the only way to prevent temperatures from continuing to increase is we need to get greenhouse gases to net zero, and we need to get there as fast as humanly possible. And that's the message I'm trying to get across here. And hopefully, if you understand how these atmospheric circulation works, you may get an appreciation for that. If you didn't see, if you're not familiar with the channel, other things, I put a QR code there that will take you to the channel directly. Right below that is a copy of what the thumbnail will look like for the first part of this series. It'd be 10A, Atmospheric Circulation Part 1. And then let me close, as I do with a lot of these, with something from my favorite Eagles song. Just do something, okay? And I've got some lyrics below that. And a couple of easy things you could do is, one, you could subscribe to this channel. I'm going to be doing a lot of additional videos here about how Earth's climate system works, and also about what happens when temperatures increases, and also what we can do to get to net zero greenhouse gases, etc. So we're just at the very beginning of this channel. And if you subscribe, that way you'll automatically get notice when new videos are coming out. The other thing it does, it helps with the algorithm, so maybe it directs more traffic to the site. Rate the video and comment. If you have any suggestions for additional videos you'd like me to do, or things I can do to improve these videos, please, we look forward to your input. I beg you to sort of share this link with your friends and family. I mean, this has got to be, if we're going to solve this problem, it's got to be a bottom-up kind of effort. Our corporate leaders and our politicians are just not going to solve this problem. They're too tied up, if you want to say, or influenced by people who have vested interests maybe in the status quo. And maybe just talk about the problem. Almost 80% of the people believe we have a climate problem. But we're not talking about it, so we need to talk about it. And then, as I said, they'll just do something. And thank you very much for spending this time with me, and I hope you'll join us for some other videos. Have a great day.